A biased die is used in a game. The probabilities of getting the 6 different numbers on the die are shown in the table below. Now, because the die is biased, it means that the probabilities of getting these numbers are different. If the die was unbiased, then the probabilities of getting each of these 6 numbers would be the same. They'd all be 1/6 actually. The probability of getting a 1 would be 1 over 6. The probability of getting a 2 would be 1 over 6, etc. You can see that they're quite different here. Now, we want to look at the expected value of the random variable x, where x is the number thrown. Now, what is a random variable? Well, a random variable takes on values. Well, in this case, it takes on the values 1 to 6, the integers 1 to 6, with certain probabilities. And those probabilities must add up to 1. So a random variable is a variable that takes on values. In this case, it's these 6 values with certain probabilities, and the sum of all those probabilities must equal 1. So for example, the probability that a random variable x equals 2 is 0.25, and so on. The probability that x equals 6 is 0.1. Now, the expected value of a random variable x, written like this, e and x in brackets, is got by summing the products of the values that the random variable can take on, which are denoted by x sub I here, times the probability that the random variable x will take on that value. And we sum all those values from 1 up to n, if there's n of them. Now in this case n is 6, there are 6 values. So in this case we're summing from I equals 1 to n. Actually, I'll just write down what we get here. This is the general formula. This will make sense in a second. If we take the first value that x can take on, we can see it's 1. We multiply by the probability that x can take on the value 1, that x equals 1. In this case, x1 would be 1. You know, if we put 1 in for I, well, that probability is 0.25. And then we add on the next value that x can take on. This would be like x2. x2 would actually be 2 in this case, times the probability that x equals 2, which is 0.25, and so on. So we multiply these values by the corresponding probabilities, and we sum. This sigma here means we sum all those products. So I've written it down up here. We just take the values that x can take on and multiply it by the corresponding probabilities. So just to explain this expression here, you don't have to worry too much about this once you know what to do, but just to see what it means. We start with I equals 1, so we get x1. So x1 would be the first value, or one of the values that x can take on. x1 in this case would be 1. And the probability that x equals x1 is 0.25. Then the next term would be got by putting 2 in for I. So we would get x2, which would be a second value that the random variable x can take on. So x2 in this case happens to be 2, but it doesn't have to be 2, it could be any number. And we multiply it by the probability that x equals x2, which is 0.25. x3 then would be the third value that x could take on. It happens to be 3 here, but it could be anything. And its probability x equals x3 is 0.15, and so on, until we get to the last value that x could take on, which is little x sub n. And the last value here is 6, and we multiply by its probability, which is 0.1. And then we sum all of these. The sigma means we sum them. And for this example, we get 2.9. Now, what does that actually mean? It means that if we throw this die many times and average all the values that come up, or get the mean of all the values that come up, we would find that mean is 2.9. So if we say threw this die 100 times, we could note down some of the values that we get. You know, we might get a 1 for the first throw of the die. We might get a 5 for the second throw of the die. Then we might get 3. We might get another 3. We might get a 2, so on. And if you can imagine doing this 100 times, and say on the 100th throw of the die, you might get, say, let's suppose you get 1. If we sum all those values and divide by 100, we should get a number that's approximately 2.9. That's what it means. And this approximation gets better and better the more throws we take. So if we take, say, 1,000 throws and add up 1,000 values that we get from throwing this die, we should get a value that's even closer to 2.9. So we get closer and closer to 2.9 for the mean of these values when we take more and more throws of this die. Now, to answer the next question, we have to consider the throw of a fair die. So before I get into this next question, I will discuss the probabilities and expected values for the number thrown from a fair die. So I'm going to let the random variable y equal the number thrown for a fair die. So that number can be any number from 1 to 6. And because it's fair, these probabilities are the same. So the probability of throwing a 1 is 1 over 6, because there are 6 options and they're all equally likely, so it's just 1 over 6. Similarly, the probability of throwing the number 2 on a fair die is 1 over 6, because this 2 is just one option out of 6, and all these options are equally likely. And of course they all add up to 1. Now what is the expected value for the number thrown on a fair die? Well, we do it in exactly the same way we did this previous calculation, of course. We take all the values that y can take on and multiply by the corresponding probabilities. So we have 1 times 1/6 plus the other value it takes on is 2 times 1/6 plus 3 times 1/6 plus 4 times 1/6 plus 5 times 1/6 plus 6 times 1/6. So we just calculate this expression. Conveniently, we can factorize, since the probabilities are all the same, we can factorize 1/6 out of all of this. We couldn't do it up here for the bias die because the probabilities were different. So we could just factorize out 1/6 and sum all the numbers from 1 to 6. 1 plus 2 plus 3 plus 4 plus 5 plus 6. And we want to multiply by 1/6. That's the same as dividing by 6. So we get 3.5. So this number is the mean of the values of the die in the long run. So if you can imagine throwing a fair die, say 100 times, and noting down all the values, the first throw might give you a 3, the second throw might give you 5, the third throw might give you 1. Imagine doing this 100 times. The 100th throw might give you a 2. Now if we get the mean of all these 100 values, that means we add them all up and divide by 100. You should find a number that's very close to 3.5. And you can imagine this approximation getting better and better if we increase the number of throws. So suppose we have, instead of 100 throws on top here, we have 1,000 throws. Okay, so we'd sum all the values we got from those 1,000 throws. We divide by 1,000, we get a number that's even closer to 3.5. So we're getting closer and closer to 3.5 as we take more and more throws of this fair die. There is a game at a fun fair. It costs €3 to play the game. The player rolls a die once and wins back the number of euros shown on the die. The sentence below describes the difference between using the above biased die and using a fair, that is unbiased die when playing this game. By doing the calculations required, complete the sentence. If you play the game many times with a fair die, you will win an average of how much per game? But if you play with the biased die, you will lose an average of so much per game. So let's look at the fair die. It costs €3 to play the game, so you pay €3. Now, on average, you will win back the expected value on the die, which is 3.5. So 3.5 is the expected value on the die, and in euros that comes to €3.50. So you win back what's on the die. So if the average value on the die, or the mean value on the die, is 3.5, it means you win back 3.5 euros. Of course, there could be anything on the die. When you throw the die, you could get a 2, which means you win back 2 euros, or it could be a 6, which means you win back 6 euros. So when I say win, it, I really mean your returns are 350. So you actually win what your return, which is 350 minus 3, which is 50 cent, or 0.5 euros or 50 cent. So more accurately, I should say your mean return is 350. So to find your winnings, you take your mean return and subtract what you pay, and that gives your mean winnings. That's your average winnings per game. Similarly then for the bias die, you pay 3 euros to play the game, but we know from the first part that the mean value on the bias die is 2.9, so that corresponds to returns of 2 euros 90 cent. So the mean return for the throw of a bias die is 2.9 euros. So your mean winnings for the throw of a bias die is 2.9 minus 3, which is minus 10 cent. Well, since we're talking about losing in this statement here, you will lose an average of 10 cent per game. So your mean winnings are your mean returns minus what you pay. So 2.9 minus 3 is minus 10 cent. That means your mean loss is 10 cent per game. So negative winnings are losses, of course.